Hi, my name is Stav Ashur, and I'm going to talk about a constant factor approximation algorithm for vertex guarding a weakly visible polygon. So let us start. The art gallery problem. The art gallery problem was posed by Victor Klee in '73, and he asked how many guards might be needed and are always sufficient to guard a simple n-gon. Now, what does that have to do with guarding an art gallery? Well, take this polygon, for example, and imagine that this is the floor plan for some art gallery with works of art on the walls and on spaces, and we want to place guards, minimum number of guards, to guard all of these works of art. So first, we need a notion of visibility. So we say that a point is visible from another point if the line segment between them is contained in the polygon. This is very intuitive as we cannot see through walls, obviously. So for example, if we place a guard at this point G1, then this striped area, all the points that G1 can see, this is what is now guarded. This is also known formally as the visibility polygon of G1. We want to guard the entire gallery, so we take 5 points, these 5 points, for example, we place guards at those points, and they guard the entire art gallery. I think that this is even optimal in this case. So you might say that no art gallery looks like this, but a counter example would be the Denver Art Museum. This is actually from the website. Some images of this building really gives motivation to computational geometers. So we can easily see a comb polygon, for example, that gives us a lower bound of n/3 guards. This is an amount of guards that is sometimes necessary. We can add a tooth by adding 3 more vertices, and each tooth needs a guard to watch over it. Okay. In '75, Shvatal showed that n/3 guards are always sufficient. So sometimes necessary and always sufficient. And in '78, Fisk gave a simple and elegant proof of this result, which basically says triangulate the polygon, guard the vertices, color the vertices of the triangulation with the 3 colors, and then take the smallest color set, for example, the green, and that guards the entire polygon. Okay, so we have these 2 definitions. One of them is the art gallery problem in the optimization version, and one is the decision version. Find the minimum number of guards, or determine whether k it's possible to guard with k guards. And as the problem gained popularity, more and more versions and variants of this problem came to be. For example, you can have different variations by the set from which you choose the guards, only from vertices or only on the boundary or at arbitrary points. There are a lot more, but you can see that these actually are different versions since, well, if I take this polygon, 1 arbitrary guard is enough, the red point in the middle. But if I want to use vertex guards, then I will need to have 1 for each tooth. So this is 3-to-1 ratio. But also I can have a 5-to-1 ratio, or a 7-to-1 ratio, or actually n-to-1, whatever ratio I want. So this is one thing. But also, some variants differ in the domain. So you can guard a simple polygon, which is just a polygon with no holes, or you can guard a monotone polygon, or an orthogonal polygon, or even a terrain, which is not even a polygon, but a lot of papers. There are a lot of papers on guarding terrains. You can view it as guarding a range of mountains. So the notion of visibility is a bit different here, but I think that you can deduce it yourselves. It's really not very different. But in this talk, I'm going to talk about vertex guarding a weakly visible polygon. So what's that? I didn't define it yet. I'm going to define it in a few minutes. So some milestones in the research of this problem. So in '87, Ghosh gave the first approximation algorithm that was a log n approximation for guarding a polygon with vertex guards, a simple polygon. And that actually was improved to log opt, where opt is the size of the optimal solution, and some methods for set cover were improved. And also, Ghosh conjectured that a constant factor approximation exists for the problem. In '98, Eidenbenz proved that guarding a simple polygon is APX hard for the case of vertex guard as well as for other cases. So this means that a PITAS is not likely to exist, but it does allow a constant factor approximation that Ghosh conjectured. Since then, only one non-trivial constant factor approximation was found. That was for monotone polygons using arbitrary guards. That was due to Kroner-Nielsen in 2013. Okay, so what is our domain? Weakly visible polygon. So a polygon is weakly visible from an edge, UV in this case, if every point of the polygon is visible from some point on that edge. You can also think of it as a polygon which can be guarded by one edge guard. That is a guard patrolling along this edge. But why is this interesting? Why are we interested in these sorts of polygons? Well, first of all, you can see that the lower bound example I gave is actually a weakly visible polygon. If a guard would patrol here over this edge, it would be able to see all of the polygon. But the reason that we chose this domain is actually different. Weakly visible polygons might play an important role in making progress towards guarding algorithms for simple polygons. How is that? Well, there was a recent breakthrough by several researchers that found a constant factor approximation for guarding the boundary of a simple polygon. This was done by decomposing the polygon to weakly visible polygons and then guarding the boundary of these. Excellent. So we rely heavily on a result we had from last year, and that's a PTAS for vertex guarding the boundary of weakly visible polygons. And today I'm going to show a 2 plus epsilon approximation for vertex guarding a weakly visible polygon, boundary plus interior. Okay, we can now begin. So first of all, a sanity check. I mean, maybe the PTAS that I've just talked about, maybe that's enough. Maybe it actually guards the interior as well. Maybe guarding the boundary implies guarding the interior. But sadly, that's not the case. We can have a polygon where the boundary is guarded, but there's a quadratic number of holes, quadratic in the number of guards, that is. So the PTAS does not, well, it's not enough. It does help us, but it is not enough. So let's start thinking. Okay, so this is a weakly visible polygon. Notice that the edges, the angles at the vertices of the seeing edge, these are both convex. That's an assumption that we can easily get rid of, but it makes the analysis and the algorithm a lot simpler. So we assume it. And if you want to see how we get rid of it, then just it's in the paper. And we take a visibility polygon of some vertex G. Now, this visibility polygon is composed of two types of edges. We have boundary edges like GX, that's an edge, which is a part of the boundary of the polygon. And we also have constructed edges like XY over here, and these are edges that are not part of the boundary of the original polygon. Okay, every constructed edge defines a pocket that is a sub-polygon of P, which is connected and is adjacent to this constructed edge. This constructed edge, for example, defines this pocket. And I didn't say, but a pocket is a connected set of points that is invisible to G, that does not see G. G does not see this. So that's a pocket. And now let's talk about holes. Now, when I say holes in this context, it doesn't mean a hole like as a polygon with holes, but an area that is not guarded, not yet seen by any guard. So if we have a set of guards guarding the entire boundary of these weakly visible polygons, holes only touch constructed edges, right? Because if there was a hole that touches a boundary edge, this means that this part of the boundary is not guarded. So this cannot be. Now, this means that since, well, the part right adjacent to a constructed edge is a pocket, that a hole is inside each of the pockets of the edges it leans on. So we say that H is leaning on these edges. And now this pocket, H, is completely inside it, the hole. And this pocket here, defined by the blue edge here, H is completely inside this pocket, and is completely inside this pocket, and so on and so on, all of these pockets. So this basically means, I mean, if you look at it from the perspective of H, all of these are actually half planes. So H is basically the intersection of a lot of half planes. And this means that H is convex. And all of the holes, actually, if we guard the entire boundary, all of the holes that we have are convex. But why does that help us? Well, in the paper, we give an algorithm to guard convex regions in a simple polygon from a single vertex. So if you have a convex region here inside a simple polygon, you have a convex region, you can guard it using one vertex. There is a vertex, you can find it in polynomial time, that sees all of this convex region. How does that algorithm work? Well, first of all, you take the point on the boundary which is closest to the convex region. And I'm going to show that this point sees all of the whole. And now, if it's a vertex, then we are done and we're happy. If it's not a vertex, you just slide it along the edge until you either reach a vertex or you have a vertex that starts blocking the visibility of S from this point. So if actually something enters your field of view, it must be a vertex, and you take it, and this is the vertex that sees the entire whole. But how do we know that Y, the original point, actually saw the entire whole? Well, let's prove it. So this is the general case. You have Y, and it's on the boundary somewhere, and S is the point that witnesses the fact that it's the closest one. Okay, but let's assume for contradiction that there is a point in the whole, call it T, which Y does not see. This means that there is a portion of the boundary on the segment YT. So this is on the boundary of the polygon. We now take S prime to be the closest point to Y prime of the whole, and we now have something like this. This is the boundary. We have Y, but it doesn't see T because another point on the boundary blocks it. Okay, now S is convex. This means that we can have a line going through S prime, call it L, where we assume without loss of generality that this line is horizontal, and Y prime is above that line, strongly above that line, and all of the whole S is weakly below that line. Okay, so the interesting parts of this drawing are these. Now, notice that if the entire S is below this line, notice that this distance is smaller than this distance, right? I mean, Y is above Y prime, so the distance between Y prime and S prime is smaller than this distance. And this means that actually Y prime is the closest point, or at least closer than Y. That's a contradiction. But you will say, rightfully, that I'm lying, and this is a false proof by drawing. But then I will say this. Okay, so let's assume that Y is below Y prime. But since I've chosen Y prime to be on the segment between Y and T, this means that if Y is below Y prime, then T is above Y prime. But this cannot be, as T is a part of the whole, and therefore must lie under the line. So whether Y is above Y prime or below it, we get a contradiction either way, and we now have an algorithm to guard a convex region. Great, so now we can take a weakly visible polygon, we can guard the vertices using the boundary using the pitas, and we have some holes, and we'll use that algorithm. But there's a problem. What's the problem? As we've said, we might have a quadratic number of convex holes. And if I'm going to try and guard each one of them by using another guard, I will never get a constant factor approximation. So we need some more analysis. Okay, let's consider this convex polygon H. We notice that it has an upper hull and a lower hull, right? And these constructed edges, I'm going to call the ones that form the upper hull, we're going to call them upper edges, and the ones that form the lower hull, we're going to call them lower edges. In the paper, it's defined a bit differently, and it's a bit more complicated, but that's only because it's for the proof that I'm not going to give here. But it's basically the same. Okay, so I'm going to claim that there are only G is the set of vertices that guard the boundary. I'm going to claim that there are at most G size of G upper edges that touch UV. Okay, let's take a guard placed at the vertex G, and it sees, well, it's true for simple polygons that when you have a point, it only sees one segment of each edge it sees. So In this example, G sees this segment here between lambda and rho, and lambda is the leftmost part of the seeing edge that is visible to G, and rho is the rightmost part of the seeing edge that is visible to G. And let's focus on this triangle here. Now, these two edges, they can be constructed edges, well, at least this part, and well, maybe this if there was something here, but this is possibly a constructed edge. Let's focus on this. Now, notice that this edge here can be an upper edge for some holes that lean on it. And as I move G into this slab defined by lambda and rho, well, now when it's inside, whenever it was outside, it would have one edge that is an upper edge. But now both of these can only be lower edges. And when it's inside, nothing changes. But as it moves outside, again, one of these can be an upper edge. So for every guard, if it's outside the slab, then it can have one upper edge. And if it's inside the slab, that's defined by rho and lambda of that point, then no upper edge. So that's the proof. But how does that help us? Let's look at the algorithm. So first we compute the set G, and then we compute all of the upper edges that have one of their points, X, like for this this point X is on all of the upper edges that have a point on the seeing edge UV. Okay, so we take for every one of these upper edges, there are at most G of these. We start looking at constructed edges that intersect them. Now, what we're looking for, and this upper edge may have some holes leaning on it as an upper edge, and this means that this is the pocket defined by this edge. Now we're looking at constructed edges that intersect this edge, and we're looking for the one with the highest intersection point. So we're going up, 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 until we find the constructed edge that crosses it at the highest point, as close to Y as possible. Why does this help us? Well, if we look at this intersection point P, and this is X prime, well, this is a convex shape. And as a convex shape, we can find a single vertex that guards all of it. And this might contain a lot of holes. And also, if we'll do this for each upper edge, we'll be able to guard every hole that has an upper edge. But every hole has an upper edge, so all of the holes are therefore guarded. Now, you will rightfully say, it's not really clear why this works or if it works. So I'm going to give you a little bit of intuition because this is all that our time allows us. So you'll say, okay, maybe there's a hole that does not have an upper edge that reaches UV. I mean, holes must have an upper edge, but it doesn't necessarily touch UV. So we have this upper edge here, XY, it's created by this vertex G, by this guard G. And there might be some hole here, H. Well, okay, but now there might be a way to add only lower edges and complete this hole, maybe something like this. But if I really try to do it, I mean, I try to add the guard that creates this edge here, I'll get something like this. And this obviously doesn't work because H cannot be inside the visibility polygon. It's a hole. But what is the problem? What is really going on here? Well, notice that UV is found here, somewhere to the right, right? This is the pocket. But if this is a lower edge, then the visibility region is actually here. So there is some point that sees only this part, but does not see any part of UV. But that's a contradiction. That's impossible because it's a weakly visible polygon. So this cannot happen, actually. The edge that is counterclockwise to this upper edge must also be an upper edge. It might look something like this. Okay, so maybe this edge doesn't touch UV as well. But if it doesn't touch UV as well, then we have the same case, and we simply do this thing all over again. So then the next edge counterclockwise also must be an upper edge, and then the next one and the next one, until finally, I mean, there are just that many edges because there are there are only that many guards. So there must be a point where this upper edge touches UV. Okay, but then why would, I mean, we found this point P, which is the uppermost point where a constructed edge intersects and all of that. But how do I know that the triangle contains all of the points, that all of the holes that lean on that upper edge? Well, it turns out that if I found an upper edge that touches UV, then the next one counterclockwise in this case, because it's a left pocket, never mind, the next one also touches UV. So if this touches UV and the next one is an upper edge, then it also touches UV. And then if the next one is also an upper edge, then it also touches UV. And this continues until you finally get a lower edge at some point. And if you draw enough figures or just read the paper, you'll be very quickly convinced that this actually means that after the process is done, no holes are remaining. This covers all of the holes that have an upper edge, and that means actually all of the holes. So what do we have? We started with a set G of size 1 plus epsilon prime, size of the optimum for only the boundary. And we added a size G prime that is at most the size of G, because for each of these G guys, there was only one upper edge, and for every upper edge, we might have added a single vertex. And the union of these two sets guards the entire weakly visible polygon. Okay, so it's very easy to see that the size is at most 2 times G, which is at most 2 times, this should be boundary, and this should be like this. Sorry for that. And this is at most 2 times 1 plus epsilon this, which is smaller than 2 times 1 plus epsilon, the optimum solution for the problem. And for some epsilon, which is not epsilon prime, this is a 2 plus epsilon approximation. So we got a approximation for vertex guarding a weakly visible polygon, and we are done. So for conclusion, just some bonus is that we can also use that to guard polygons that are weakly visible from a chord. The definition is very similar, just the patrolling guard is working on some chord of the polygon and not necessarily an edge of the polygon. But the first part of, so you just use slight adjustment, but the first part of the algorithm, where we found the guards that guard the boundary, well, the best that we have here is the general algorithm for guarding simple polygons, so that's a 27 approximation. So we get, because of the adjustment, it's 3 and not 2, but that gives us a 81 approximation algorithm for the case of weakly visible from a chord, but no constant factor approximation was known so far, so that's that. And some open problems. Well, is this problem NP-hard? That's not clear. Very similar, I mean, if you add holes to the polygon, if it's not a simple weakly visible polygon, but a weakly visible polygons with holes, then I think it's even APX hard, but it's not really known about this problem. So maybe as a first step, finding a PITAS will be a big improvement. That's very interesting. Or maybe we can find a constant factor approximation for point guarding weakly visible polygons. That would also be very interesting. But obviously, the most important and the problem, the result that we wish for, and might actually be close due to some efforts from Gosh, is finding a constant factor approximation for vertex guarding simple polygons. That's sort of the holy grail in this case, I might say. And that's it. Thank you very much. And now I guess it's time for questions.